Right, let me find some chalk. So I thought I'd begin with a sort of recapitulation of the Hopf argument that I did at the end yesterday. And then the idea of this lecture is to talk about how to do it if you had variable negative curvature instead of just negative curvature. And then tomorrow we get to how to do it if you have the Weil-Petersson metric. So I will have, let's see, I think M can be a compact manifold. Actually, maybe let me just say hyperbolic. So constant negative curvature, which might as well be -1. But the argument whether it's dimension 2 or dimension n is the same. So it can be dimension m this time. And so you've got the geodesic flow acting on the unit tangent bundle of em, and we want to prove that this is ergodic. So what we're supposed to do is to prove that a measurable invariant function, an L1 invariant function, is almost everywhere constant. And there's the sort of measure theoretic arguments that I sketched last time, which reduced the problem first to showing that Birkhoff averages are almost everywhere constant, and then to showing that the Birkhoff average of a continuous function is almost everywhere constant. So let's have f from T1m to R be continuous, and therefore uniformly continuous because of the compactness. And what we need to show is that the two Birkhoff averages are almost everywhere constant. So let's just say almost everywhere constant. And this is with respect to our Liouville measure mu. And so just as a reminder, the forward average of, say, a vector v is the limit as big T goes to infinity of 1 over t times the integral from 0 to t of f of vtv dt. F hat minus is the corresponding average, except that you go backwards in time. And Birkhoff says that there is a set G in the unit tangent bundle. Maybe I could say that the measure of G complement is 0, so it's almost everything. And if V is in G, F hat plus V, F hat minus V are defined, and they're equal. So that's the basic setup. And then we can look at a picture of the universal cover of our surface EM. So this is the universal cover of EM. And if I have a vector V in the unit tangent bundle of EM, I can lift it to a vector V tilde that's tangent to the hyperbolic plane. And it doesn't matter which lift I pick, the construction that I make will look the same. And then I can draw the two, well, there's the geodesic, and then there are two horospheres. Of course, the picture looks exactly the same as the picture I drew in H2, because I only draw in 2 dimensions. And then we equip these horocycles with the unit normals that point on the same side of V. And this defines the stable and the unstable manifold for V tilde. So maybe blue is WS of V tilde. It's all these vectors pointing inwards. And there we have WU of V tilde. And so I could make this construction for every vector tangent to the unit, tangent to HEN. And what you would find is for each point at infinity, I would have the collection of Horospheres. And so, well, these Horospheres, for each point at infinity, the Horospheres foliate HEN, and then you have the normals to them. And if I fix a point in HEN, if I look at the different directions through it, as the direction changes, the point at infinity changes. And so you can see that every vector that's tangent to HEN belongs to one of these WS sleeves. And you have a nice picture of the leaves foliating, in this case they're foliating T1HN. And then the foliation of T1HN projects to a foliation of T1M. And so by foliation, what I mean is that if I look locally, if I have a foliated manifold, I have a neighborhood in which I see leaves of the foliation. And then there's a map that's at least a homeomorphism, and it straightens this picture out to a picture of a foliation of a box in Rn being foliated by parallel copies of Rk. So sort of Rn equals Rk cross Rl. So this is the Rk direction. That's the complementary direction. So locally, your picture looks just like the pages of a book or the lines on your sheet of notepaper. So we have that set up. And so we get actually 3 transverse foliations. They're usually denoted WS, W0 is convenient. So this is this is the stable one. So these are the vectors that flow forward towards the same point at infinity, and they approach each other exponentially. So you get exponential contraction. And WU is the corresponding thing, except you go backwards in time. So again, you have exponential contraction. But when you flow in the reverse direction, and W0 is the orbit foliation. You can also combine these two to have a weak stable foliation and a weak unstable foliation. So the weak stable foliation corresponds to, for each point at infinity, you have a weak stable and a weak unstable foliation. The weak stable foliation here is all of the vectors perpendicular to all of the Horospheres for this point, and the vectors pointing towards this point. So all of the tangent vectors to all of the geodesics that end up at that point at infinity. So that's the sort of structure that we have. And then we make this argument in the unit tangent bundle. Oh, by the way, it might look here as though there's a tangency between the stable and unstable leaves. But what you're seeing is a tangency between the stable and unstable Horospheres. The Horospheres have to be tangent because they're both perpendicular to the same geodesic. But these these manifolds are not tangent in the unit tangent bundle because the one horosphere curves in one direction, the other one has curves in the other direction. So the manifolds of vectors are not tangent to each other. The apparent tangency in the picture is a little deceptive. And so then we make the argument that we start with WU is in fact, it's a C infinity foliation. So my foliation, so the foliation is a CK foliation if the smoothing out map can be chosen to be CK. And in the case of the foliation that we've constructed with the unit normals to the Horospheres in HN, actually I think we get even real analytic, not just C infinity. Yeah, so you can straighten out the foliation with a C infinity diffeomorphism to the standard picture. And so now we pick in fact, it's a typical leaf, say WU of V0. Such that G intersect WU V0 has full, I'll say, leaf measure. And so what I mean by leaf measure is I have my foliation and each leaf in the foliation is a submanifold of T1M. I have a Riemannian metric on T1M. I described that last time. You can restrict that Riemannian metric to each of your leaves, and then you get a Riemannian volume on the leaf. That's my leaf measure. So this is Riemannian volume on the leaf. And the main thing I care about with this measure is the difference between measure 0 and positive measure. So any effort at getting a reasonable smooth measure will do here. So I have my nice leaf WU of V0 and my set G. I will draw only some selected points from G. In fact, almost all of that leaf is in G. And on this leaf, I know that I think I forgot to mention perhaps the most important step is that F hat plus is constant on WS leaves, as we saw last time. F hat minus is constant on WU leaves, and they're both constant on W0 leaves. So I look at my WU leaf and I can say F hat minus is constant. I can say from that F hat plus is constant on G intersect WU V0. So I have a common value for F hat plus at all of those green spots. Then I can extend the WS leaves through here. And F hat plus is constant along all of those. Maybe I should draw these in green. So on all of these green leaves that I've drawn, I have a common value of F hat plus. And there are a lot more green leaves than I've managed to draw. Basically, it's almost everything in the blackboard picture. And then you've just got the flow direction transverse to this, along which F hat plus is constant. So you've now got a whole neighbourhood. V0 is in here somewhere. You've got a whole neighbourhood of V0 in which there's a full measure subset on which f hat plus is constant. And so that's the argument. And so now we want to do the same thing if we have variable negative curvature. And a lot of the argument goes in exactly the same, well, almost exactly the same way. I had a picture, I'm going to have a picture of the universal cover, so maybe I should set up a context of what we want to talk about now. So we will have MG compact and Ramanujan, and our metric G has negative sectional curvatures. Right, that is the setup, and we want to show that the geodesic flow on T1M is ergodic. So the first step is that M tilde, the universal cover, is again a disk. And then there's going to be a really completely similar picture of horospheres. We're going to construct, there will be WS, W0, WU, and all with the same properties. So I should say a few words about where this stuff comes from. So the usual construction of the horospheres in hyperbolic geometry is you draw the Poincare disk, and then you draw Euclidean spheres tangent to the boundary of the Poincare disk. This is a little difficult to do in our M tilde here. This is just some complete manifold that's the universal cover of M. There's no Euclidean anything. We don't even yet have a boundary sphere. So you have to go and create those things. So I think I'll spend a little bit of time talking about just the beginning ideas about how you get started with getting from negative curvature to being able to say it's the same picture really as hyperbolic space, as you have in hyperbolic space. And then I will come to what goes wrong and why we have to work harder. So let me start with really saying something about how you can see the effect of negative curvature on the geodesic flow. So what I want to talk about actually is, I want to say something about the derivative of the geodesic flow and how you can think about that. And this, of course, is useful in any investigation, it's more or less essential in any investigation of the geodesic flow. So okay, so well, let's start with an abstract picture of what the derivative of the geodesic flow means. And this is really basic stuff. This is just, what do you mean by a derivative? So I've got a V somewhere in the unit tangent bundle. I've got the orbit of V. I now have a tangent vector to the unit tangent bundle. And I want to see what the derivative of the flow does to this tangent vector. Well, what do tangent vectors do for mankind? They exist to be tangent to curves. So we have a curve. This time it's going to be V of S. That little v will still be big V of 0, and of course xi is the tangent vector at time 0. And now each of these curves can be, each vector, each thing along the curve can be flowed along. So somewhere here we have phi sub t of big V of s. So you get a bunch of curves along here. And each of these curves has an initial tangent vector. And the one you see here is the derivative of phi t, I guess, at V acting on xi. That is just an abstract picture of what the derivative of a flow means. And it's conceptually good, but not entirely helpful. So it's much more useful, really, to draw the corresponding picture in the manifold. We've seen this before. So now I have my vector V has a foot point, which you won't be surprised is P for point. We have P, we have V. We have the geodesic for V. My curve in the unit tangent bundle now looks like a vector field along a curve. There's V of S, V is equal to V of 0. Each of these curves has a geodesic. This will be gamma sub Vs of t. And I think I will give that a name. I'll call it alpha of St. And if you've done any Ramanujan geometry, this is a rather familiar picture. This is a picture of a one-parameter variation of a geodesic. The geodesic in question is gamma sub V. Here are the geodesics from the one-parameter variation. And what you do in this picture is you calculate d alpha ds. You like to do it with s equals 0, so you get the infinitesimal variation at your geodesic that you began with. And by doing it at t, you find out what's happening distance t down the geodesic. And we could call this j sub t. The reason for calling it capital J is this thing is what's called a Jacobi field. And there is a calculation that you do. Which is the easiest thing to do is to know the equation that this Jacobi field satisfies, and then to start with the left-hand side of the equation and turn it into the right-hand side of the equation. So the Jacobi equation, actually everything's on the, well, here's the equation. Of course, is the Riemann curvature tensor. And gamma, this should be gamma V. This is the tangent vector to the geodesic. And what you do to prove this is you start with this thing, which is a couple of covariant DDTs acting on this. And then you start reversing orders of differentiation. And there's at least one of them where the curvature appears and you end up exactly with this. It's a more or less self-working proof and it takes half a page. Great, so you get this equation. And you can see that it's a linear second-order equation along the geodesic. So the sort of, if you know J and its covariant derivative, so J prime of t, which will be partial ddt of d alpha ds. That's the sort of data that comes out of this equation. And now if I go back and look at, well, if I think about what I have in this picture and relate it to the setup here, the curve that I drew here is this curve of vectors. It's d alpha it's d t at st. It's that curve. And if I differentiate, so now the data, this guy here is the tangent vector to this curve of vectors. So d phi, this thing is going to be a pair of vectors. The first vector is going to be the derivative to the curve of foot points. That's clearly the vector in this direction. It's going to be d alpha ds at 0t. You can see it's this thing. And what's the other piece of data? Well, you take the derivative of the covariant derivative of your vector as you go along the curve. So the other piece of data is going to be ds of d alpha dt at 0s. And you can, symmetry of the connection says you can just reverse the order of differentiation. And so, lo and behold, you find that this is just the Jacobi field and its covariant derivative. So if I have a vector, if I have V in the unit tangent bundle and I have tangent vector xi, it will be xi and its derivative under the geodesic flow. And corresponding to xi will be a Jacobi field. And you will have j xi at 0 being equal back to the horizontal part of xi, and the initial derivative will be the vertical part of xi. And d phi, when I apply the derivative for time t to xi, what I get is j xi at t, j xi prime at t. So derivative of the geodesic flow can be understood by investigating Jacobi fields. So this step of reversing the order of differentiation here is the sort of key insight in seeing that you can do it. So that's great. That allows you to use geometry to figure out what the derivative of the geodesic flow does. And it also allows us to see what negative curvature does. So let's assume that sectional curvatures are negative. And let's assume that J is a Jacobi field along a geodesic I'll call gamma. So what I want to do is to look at the norm squared of J. It's always better to look at the square of the length rather than the length itself. Maybe if I was clever, I'd look at half the length of it. But if I take this and differentiate once, I get twice in a product of J with J prime. So let me actually put a half there. And I'm going to look at the second derivative now. And I don't want lots of 2's over on the other side. So what I've got on the other side is J prime prime. And this is J prime plus J double prime. And J double prime, we know what that is from the Jacobi equation. And I think I'll reverse the order of these terms, which is fine because of symmetry. So I get J prime minus the inner product of Rj gamma dot with J. Now you look at this, and the sectional curvature, at least with the way I set things up, this is exactly, well, it's almost a sectional curvature. If these guys were orthonormal unit vectors, it would be a sectional curvature. So it's actually the sectional curvature for the plane spanned by these guys, scaled by the area of the quadrilateral that they span. Anyway, it's sectional curvature, which is negative times -1 times something that's positive. So what we get here is greater than 0, and it will be, well, unless J prime equals 0 and J equals 0. So what you discover is that negative sectional curvature means that the length squared of a Jacobi field, any Jacobi field, rather than the one that's always 0, is going to be a strictly convex function. And you can reverse the argument and show that, so this convexity property of Jacobi fields is equivalent to negative curvature. So after this, you can the curvature tensor itself can kind of disappear into the background, and you've got this sort of convexity property to work with. So that's, I think, about as far. Oh, there's maybe one more little calculation I'd like to do, just so, because I think it would be quite helpful. Suppose I know. Suppose I know that this is positive. Well, you can see from our convexity that once this thing becomes positive, it's going to stay positive, and it's going to get bigger. And in fact, you'll get J prime, or what you'll get, this will be greater than or equal to J prime plus, and I will assume that the Jacobi field is perpendicular to the geodesic. So this term here will look like plus k squared, at least plus k squared. So the area of the parallelogram here will be the length squared of J times the length squared of gamma dot, which is 1. So there's the length squared of J, and I will assume that the sectional curvatures of all planes are less than or equal to minus k squared. And then there's the Cauchy-Schwarz inequality or something like that. And this will be greater than or equal to, I think, 2 times, I think it's the minimum of 1 and k times the inner product of J with J prime. So the point is that I want to make is I get a differential inequality, which said, whoops, there was a derivative there that I forgot, that the derivative is greater than or equal to a positive constant times thing. Or if you like, if I divide both sides by this, the derivative of the logarithm is greater than or equal to a constant. So this thing is going to grow exponentially once it becomes positive. So we have, these are some basic effects of negative curvature. And I think that's enough of actual calculations. I think I can just wave my hands a bit and say things. So if I go back and look at the universal cover, so let me make a space for let's have a sort of blank slate for our universal cover. I pick a point in the middle of it. I look at some geodesics radiating out from this point. I look at the one parameter variation through them. This is going to be something where the Jacobi field is initially 0 and has a derivative. My Jacobi field is going to start growing in length. So I'll have J prime. The inner product of J with J prime will be positive. And then it's going to grow exponentially. So my geodesics radiate out from the point, and the distance between them grows exponentially. So you can see from that the exponential map at any point in the universal cover is actually a diffeomorphism. So your universal cover is going to be diffeomorphic to a disk. In fact, it's diffeomorphic to each of its tangent spaces. So that's the start of the recovering the picture of that resembles the Poincare disk. The next thing is that you would like to construct horospheres. So you construct horospheres. I think we can erase this. Horospheres are the limits of ordinary spheres. In the universal cover. Suppose I have a geodesic in the universal cover going off to infinity. I can go to, say, gamma of t. I draw maybe t1. I draw the sphere of radius t1. I go further and I draw a bigger sphere. And I take a limit as Tn goes to infinity, and I end up with a limiting sphere. There's an easy calculation with the triangle inequality that shows that these spheres are nested and that you get a limiting sphere. So you can construct horospheres that way. And then if I think about the sort of infinitesimal version of this picture, if I have a sphere that was centered there, it's a variation. I have a variation of gamma through geodesics that all go through that point. So I'm looking at Jacobi fields that start off with some value here and then shrink to 0. And they're going to shrink monotonically until I get to there. And then if I take a limit of this picture and end up with the horosphere, I'm going to get geodesics that are, at the very least, not getting any further apart. And then it's easy to see that, in fact, they are collapsing exponentially. If I go the other way, I'm tending to see exponential growth from the little calculation I did over there. And so if I have the geodesics perpendicular to my horosphere, and I go out here and then come backwards, the corresponding Jacobi fields and therefore the actual distances between the geodesics are going to grow exponentially. So I can recover the picture now of, if I think of, I think I want another picture of my horosphere. Let's make some room for it here. The derivative of the geodesic flow has done its work for us. I think I will now just draw the picture of the universal cover with its boundary. And the way I can define the boundary is if I have a vector v, I can think of the geodesic going off to infinity, and then I have a horosphere. And the geodesics perpendicular to the horosphere approach this one exponentially as you go out. And so I can just imagine that I can decree that the point at infinity is this equivalence class of geodesics that are approaching each other exponentially. And you can glue things together and you get a nice completion of the universal cover as it turns into a closed disk with a boundary that's sensibly related to the interior in exactly the way that you're used to from the hyperbolic plane. And so you recover the whole picture that you had in the hyperbolic plane of horospheres, and we have stable, unstable foliations for the geodesic flow. You have the same kind of exponential expansion and contraction. It's all great. We have every ingredient in the proof. What could possibly go wrong? Well, there is a slight difficulty. I said, I made a point that the stable and unstable foliations in the case of the hyperbolic space were C infinity, or in fact even better. It turns out when you investigate, or if you work with surfaces of variable negative curvature, you can prove that the foliations are C1. Eberhard Hopf did that. And so that allowed him to prove that the geodesic flow for a compact surface of variable negative curvature is ergodic. He stopped at that point. I assume that he intended to prove that the foliations were at least C1 in higher dimensions, but he never did that. I think the reason is, well, it's probably a good thing that he didn't, because it's just not true. And Nosov actually gave an example to show that it is not true. It's really not true. So you do not have even C1ness of these foliations. You only have, well, they are Hilda continuous, but not better than that. And so in the picture that has now disappeared of, maybe I'll restore it, you have a picture of a foliation, and you apply phi to it, and it straightens out to, say, the standard foliation of a box by parallel slices. And you want to make the argument that if I have a full measure set G here with full measure, I want to be able to say that almost every leaf intersects G with full measure in the intrinsic volume of the leaf. And if I go over to here, there is phi, big phi of G. If this map is C1, if this is a C1 diffeo, okay, it doesn't have to be volume preserving or anything, but it's going to take measure 0 to measure 0. So we will have a full measure set G, phi of G over here. And now I can use the usual Fubini theorem on this picture, say that almost every one of these vertical leaves is almost entirely inside my full measure set. Then I can take one of those leaves and pull it back by phi, and the complementary set that wasn't in this good phi of G has measure 0. After I've applied phi to it, you still have measure 0. So everything works beautifully if I've got a C1 diffeomorphism. If my straightening out map is not C1, well, perhaps there could be a problem. And the answer is yes, there can be a problem. And this was appreciated, I think, already by Hopf. It was certainly well known to people in Moscow. So it was really Kolmogorov. He gave an address to the ICM, I think in 1954, in which he said sort of these investigations of Hopf should be pursued further. And then he had a couple of bright young guys. One of them was Sinai, and in particular in this geodesic flow question, Anosov, and they actually worked things out. So they certainly knew that there were problems. I don't know if they had an explicit example, but later I remember a conversation in 1992 when Anatoly Katok was asked, can you show an example of the problem actually happening? And just without pause, Katok described an example. I assume that he had worked it out sometime before, maybe even years, decades before. Or maybe he just worked it out on the spot. And then eventually, after a few years, this example, everyone got to know this example, and they all made up their own versions. There's a central trick behind Katok's example, and everyone made up their own version of it. And there's a paper called Fubini Foiled, and then I think there's a subtitle, Katok's, I think, paradoxical example. Katok never published this thing. I guess he asked his publicist to do it. The paper's by John Milner. It's in the Mathematical Intelligence, maybe from around 1997. If you do nothing, if these lectures motivate you to do nothing else, go read that paper. It's about 3 pages. It's in the John Milner style. Everything is there, but it's lucid, it's easy to read. It's great. So what does Milner have in this paper? He has an explicit foliation of the square, and I will just vaguely sketch what it... There's a reasonably nice picture, better than that one. And you have real analytic curves. You have a C0 foliation. You have G contained in S with area 1, full area. And now comes the punchline. G intersects each curve in at most 1 point. Just digest that for a moment. That set G, if I drew it, would just look like I'd shaded in the entire square. And yet, if you follow one of these curves, it hits the set in possibly 0 points, but no more than 1. So if you attempted to do this Fubini business with that foliation, just abysmal failure. It's this failure is as total as it could be. So you're up against that sort of thing. Right, so you cannot prove that the foliations we're interested in are C1 because they're not. You are not going to exploit they do in fact have reasonably nice leaves. The leaves are about as nice. If you started with a C infinity manifold, you have C infinity leaves. But the way in which they vary is, okay, this foliation is actually better than C0. He doesn't actually prove that it's C alpha, but it is for some alpha that's less than 1 though. And that's the setup we have. So sort of general theory about smoothness of foliations is not going to help. You have to give some kind of direct proof that you can do what you want to do. So the only step that is difficult is the step of showing that you can, given the full measure set, you can select a nice leaf that intersects the full measure set in full measure. And if you analyse what's going wrong in examples like this one, the sort of thing that's going wrong is you have places where the leaves that were reasonably spread apart here get very, very bunched together there. So if I draw the 2 transversals and look at the transition map, there's a tremendous contraction of volume. Or if I go the other way, there's a tremendous expansion. And if you look in the right places in this picture, you can see worse and worse behaviour like that. So it turns out that the property that you have to prove is the following one. So suppose we have a foliation W. W is what's called transversely absolutely continuous. If, let's say, for each alpha positive, you say alpha positive, maybe I will state it imprecisely. I will just say I will say there is a uniform bound on the Jacobian of its transition maps. And you have to do a little thinking to understand what I mean by uniform, because it's easy to draw pictures in which I can make this Jacobian as big as I like. So what I mean by the Jacobian is, well, I have my foliation. I then put in two transversals to the foliation. And now I look at the transition map. And I look at some, say, small disk here and the corresponding image disk. And I compare their sizes. So I look at the supremum over sort of small disk contained in T of the volume, the transition map I'll call pi, volume of pi of D divided by volume of D. And you want to have a uniform bound on what this can be. Well, you have to be a little, you have to ask for something reasonable. If I allow the transversals to be way, way apart from each other, obviously the bound will have to get worse. If I allow the transversals to be only just transverse and making a very, very small angle with the leaves, obviously I can make this supremum as big as I like. So I have to put in some words here about uniform bound on the distance between the transversals and uniform transversality. That's sort of within reason. For reasonable transversals, you want a uniform bound on this. That turns out to be the heart of the matter. Once you can do that, you can run Hopf's argument just the way Hopf did it. And so what these guys did was they went and proved that directly for the type of foliations we're interested in. And it's written up in a book that Nosov wrote. And I don't recommend trying to read a Nosov's book. I asked some of the slightly younger guys who were part of this group, where actually they told me, yeah, when we were trying to generalize this, we didn't read the book. We just got a Nosov to explain it to us. The book I would suggest where it is written down, there's a textbook by Brin and Stark where they actually write down the argument. And so now I want to give a sketch of the ideas that go into the argument. So let me see what I can do. So I have my flow acting in the unit tangent bundle. One of the unfortunate things is this argument, I'm talking about flows, and the flow direction is a nuisance in this argument. I want to get rid of it. So what I'll do is if I have my orbits of the flow going this way, I'm going to think of drawing a transversal to the flow. And then I have my leaves WS, W0, WU. And rather than thinking about these guys, I am actually going to take, say, the weak stable and intersect it with the transversal, and the weak unstable and intersect it with the transversal. And then in a transversal to the flow, I am going to see two foliations. So blue will be actually WS0 intersect my transversal, and I'm just going to call that WS. And the orange will be WU0 intersect the transversal, and I'll call that WU. And I'm going to deal with this picture. And so now I want to think about why, and now I'm going to look at the transition in this picture. There's going to be, I used T. All my transversals are called T. what's another word for trends? It can be X. Now, inside here, X, I will have T and T prime. And I'm going to look at the special case where I'm going to be looking at the stable foliation WS and the transition between two unstable leaves. Really, I've got to look at more general transversals, but doing that adds details rather than real idea to the proof. And now the idea in the proof is you can sit and stare at this picture for as long as you like, and you will learn nothing. What you need to do is actually redraw the picture down here. I didn't bring the coloured chalk with me. Oh well, we have our X, our T and our T prime and our WS leaves. And now this isn't just a picture of a foliation, we've got a flow. So we apply the flow, and we apply it for a very, very long time. And we keep flowing and flowing and flowing till we get over to here. So this is phi sub t of x for some enormous t, and actually it will be convenient to use integer increments of time. So this is phi sub n of x for some really big n. And now what happened to that picture? There were some vertical, I'll get the coloured chalk, there were the vertical guys that were meant to be blue. They're stable. They're contracting exponentially. There are horizontal guys that are unstable. They expanded exponentially. So our picture now looks like this, except maybe even more so. Okay, maybe I'll come back to now you've got this enormous stretch out. And so now let's come back maybe to the middle of the board and talk about what I'm going to do. What you want to do is to build a succession of approximations to the holonomy, which will be differentiable maps for which we can take the derivative. So we want to build a sequence of maps Pn from T to T prime such that Pn converges to P, and what I'll call the Jacobian of Pn is uniformly bounded. And the bounds on here will come because we've got derivatives. We can bound derivatives. So how do I build PE? And I have my initial picture of, I apply phi sub n to get my new picture. And now what I do here is I just pick some smooth approximation to going vertically. Maybe I'll call this pi. And so Pn is going to be, I do phi sub n, I do pi, I flow backwards. And then if I work out the Jacobian, it's just going to be a sort of, it's going to be the Jacobian of this composition. And now the Jacobian at each point is a number, which tells you how volume got multiplied. And we're just working, we're doing this for the derivative, we're looking at how the derivative of these maps are all differentiable. We look at how their derivatives multiply volume. So for each of these maps, we have a number. And the result, it's going to be just a product of like that. And this number in the middle is always going to be a perfectly reasonable number. The problem is there was a minus sign there. This number is enormous, and the bigger I make it, as this grows exponentially. This is some approximation to the inverse of the number here, but it's sort of 1 over an enormous, exponentially big number. So there's lots of potential for things to go wrong. This is a little uncomfortably like sort of trying to do 0 divided by 0 or something like that. But it helps that you can, since these are numbers, I can change the order in which and also I can think of phi sub n as phi1, flow for time 1, do that n times. And so I end up thinking about a product. What I have is something like I have the Jacobian, whatever it is, some number for pi. And then I will have a product from k equals 0 to n minus 1. And then I will have some number, which I'll use absolute value signs for it. I have the derivative of the time 1 map of the flow acting at phi sub k of now I have some point v here, phi sub k of v, and then I have this derivative restricted to the tangent space to W U. I have a number like that. And down below I have a very similar number. When I come back, I'm using the inverse map, and the multiplication factors for the inverse map they're just the inverses of the multiplication factors for the forward map. So down below I will have the same kind of thing, except some vector W, which will probably be about there. So what happens is here I get, in this picture I have phi sub n v. I then do pi phi sub n of v. I then come back to W. That tells me what W is. So I have a product like this. This is not quite an infinite product, but it's kind of close to it. Anyway, the idea is you should really think of an infinite product here. And then what you'd like to prove is, if you were thinking of an infinite product, you'd be wanting to prove that it converges. And convergence of products, or keeping them under control, the way you do it is you take logarithms and convert it into a problem about sums. So really I have to look at the sum from k equals 0 to n minus 1 of the absolute value of log of, I'll just say what we have at phi kv minus the absolute value of log of what we have at phi k w. I have something like that. And what allows you to control this sum is that the distance from phi kv to phi kw shrinks exponentially as k goes. This is less than or equal to some constant times some number lambda to the k, with lambda being less than 1. Because if you look at the picture, W is not the point, the image of the actual holonomy. The actual holonomy gives you maybe V dash, this would be phi sub n of v dash. But now the distance here is very small, and as I iterate backwards, it shrinks exponentially. So actually W is extremely close to what you would get from the actual holonomy. So we more or less think of W as being V prime. The error involved in doing that will not affect anything. And then V and V prime approach each other exponentially as you iterate forwards. So we get an estimate like this. Now there is a technical step that I completely omitted in the interests of time, so I could save myself about 2 minutes to finish this proof. The tangent space to WU varies Hilda continuously. And you can get a uniform Hilda estimate on it. So that means that the distance between, so if I look at, and so this means that log of d phi k, d phi 1, let's say some vector u restricted to tangent space to WU, this kind of thing that we're looking at in here, this varies Hilda continuously. So that means that this term in the sum is less than or equal to some constant times the distance from phi kv to phi kw to some power alpha, with alpha being between 0 and 1. And then because of the estimate on the distance, this is less than or equal to some constant times lambda, product of probably two constants, times lambda to the alpha k. And lambda is less than 1. Lambda to the alpha is less than 1. We've got, this is exponentially contracting. So this sum is a sum of exponentially contracting terms. And the estimate on the exponential contraction is uniform. So it doesn't matter exactly, it doesn't matter what En is, doesn't matter exactly what V and W were, as long as they're not too far apart and so on. I just get uniform exponential contraction of these terms. So this sum miraculously converges, and that says that this product that we had here converges, and so my claim that this thing converges, and that gives us the bound on the Jacobian for the actual map P. Okay, so I think I have just a couple of seconds. I think I got started just a little late. So when I've got, it says 140, what does it say? Oh, it's counting down. Oh, I've even got, wow, actual time left. So I wanted, there was a lot of details that I skipped. You're probably glad I did. But buried in those details are the fact that you need some things to make this proof work. You need enough uniformity on the estimates that went into everything. And those estimates are all, getting uniform estimates is fine if you've got a compact environment, because everything in sight is continuous on a compact manifold, so it's uniformly continuous. Everything is good. Suppose I tried to repeat this proof for a surface with negative curvature, like the once punctured torus. Suppose I have a metric of negative curvature. You can make this curvature very, very close to -1, say between -1 minus epsilon, -1 plus epsilon. It's very close to -1. And we can assume that we can arrange that this surface has finite area. So the cusp is very similar to the hyperbolic cusp. But suppose I have no control whatsoever on the derivative of the curvature, and that somewhere as you go out in this cusp, admittedly over a very short distance, you might have really violent derivative, just uncontrolled. Can you carry through this proof? The answer is no. And the guys who did the proof they were aware that it didn't work in this case. So even for something as simple as a surface of finite area, there are still open problems. Of course, if you have the kind of uniform bound, so you need the bound on the curvature and the derivative, because what goes in, they control the derivative of the geodesic flow, and then you also need to control how the derivative of the geodesic flow varies. And you need up to derivative of the curvature to do that. So, of course, if you have the kind of bounds that compactness of the manifold would give you, the proof rolls through in the same way. Without those bounds, the proof does not roll through. And so that tells you the kind of things I'll be talking about tomorrow. Because sure enough, Weil-Petersson is a Ramanujan metric with negative curvature. But do you have the kind of uniformity that I just talked about? No. So you have to get around that. And so tomorrow I'll say some things about, I will basically refuse to tell you exactly what Weil-Petersson metric is. I will tell you some properties that are known. I'm not going to prove them. Every property is basically a difficult theorem, not proven by me. So I will just tell you some things, and then I will actually finally at the end I'll be able to say something reasonably easy about how you can reduce what looked bad to something really no worse than this. So that's what will happen tomorrow. So thank you.